In episode 42 of Mobycast, we continue our conversation on DynamoDB, this time diving deep into its architecture and components. Welcome to Mobycast, a weekly conversation about containerization, Docker, and modern software deployment. Let's jump right in.
Welcome, Chris. It's another episode of Mobycast.
Hey, John. How you doing?
Good. So we're missing Rich today. Hopefully we'll be able to put this together. His producer talent is much needed. And when we don't have him, I do feel just a lack of proper orientation. But we got to get this done this week. So we're charging on without him. So we'll see you next week, Rich.
Sorely missed.
Yes. So yeah, we've been doing a series on DynamoDB. My favorite episode of the series was the first one when you talked about just your own personal relationship with the world of internet scale databases and how you did a startup that built a product which DynamoDB later referenced as prior art. So that was my favorite. And then after that, we did one just about kind of what DynamoDB is all about. And we got into, a high level overview of it. And essentially the database elements we talked a lot about last time, about tables and item, partition keys, sort keys, and secondary indexes we talked about as well. I think that just even saying that this time, I do feel like I have more to learn there, and I may need to even myself go back and listen to what we talked about before. But this time we want to talk more about the architecture and components of how DynamoDB is put together. Before we do that, one last thing that we talked about last time is partition keys and global secondary indexes and how they determine how data is partitioned across storage nodes. I think that is going to be sort of fundamental to talking about the architecture. So I think if we keep in mind that data is partitioned across storage nodes and that's a key feature of being able to scale out as opposed to scaling up, then having that in mind, this episode will talk about the architecture. And I think that concept will come up, probably again and again. Wouldn't you say, Chris?
Yeah, it's a lot of those database elements that we talked about. It'll definitely reference the architecture, and the architecture decisions and the components that DynamoDB has directly support that.
Right, and I think one of the things that'll be nice about today's episode is talking about how the whole database is put together. As we continue to talk about tables and items, partition keys and sort keys, understanding how the database is built will help us understand those things. Because I think as a user, if you don't get into understanding how the thing is put together, then some of those definitions, like what is a partition key, feels a little abstract. So yeah, let's talk about the real stuff under the hood. It looks like our first thing to talk about is just, we're going to talk about the architecture and components. And it looks like the first thing you've listed here, Chris, is the request router.
Right. Yeah. So maybe just to pop up a little bit. So
Sure.
We've talked about reInvent. Both you and I went there and attended a lot of interesting discussions. This whole series was kicked off based upon, in part, Werner Vogel's keynote, where he talked about his first day at Amazon. And so, again, thousands of sessions there at reInvent. One of the ones that I went to was titled Amazon DynamoDB Under the Hood, How We Built a Hyperscale Database. And so when I saw this in the catalog, I was like, oh, this is awesome. This is really great. So what it was a talk by one of the senior principal engineers there on the DynamoDB team, where it promised to disclose for the first time the underpinnings of DynamoDB and how we run a fully managed non-relational database used by more than 100,000 customers. We cover the underlying technical aspects of how an application works with DynamoDB for authentication, metadata, storage nodes, streams, backup, and global replication. So this was kind of it felt like a real privilege, a treat, where Amazon was opening up the kimono, if you will, and really just given a deep dive into how DynamoDB has been architected and constructed and how it works.
Mm-hmm.
So I was very interested in this, given my background as SQL, and to be able to kind of see okay, how does this compare and contrast? So that's what we'll talk about today, is basically kind of a recap of that session, going into the various components of the system that they talked about in this particular session.
All right, wonderful. Yeah, I'm excited to do it. So get us started.
Sure. So first off, we can talk about just high level the components that make up DynamoDB. And so for our purposes, to kind of keep it high level, we'll talk about there's four components that we'll discuss. So one is the request router. The request router is basically the frontline service that receives requests and handles them and is responsible for basically all the primitives that DynamoDB supports. Another component is the the storage node. So these are the actual services that are responsible for persisting data and for retrieving it.
Okay.
Then there's the partition metadata system. So this is the part of the system that keeps track of what data is where, right?
Okay.
Which is super important. It's basically that's what glues together, that allows the request router to know what storage nodes to talk to. So that's a pretty key part of the system.
Okay.
And then another the other component that we can talk about is they call it auto admin. And so this is kind of like a management component to the system that does all the housekeeping that's necessary for managing a system like this. So it does things like it deals with partition splits, and we'll talk about that, like what that means, making sure the metadata is up to date, provisioning tables, a bunch of other things. But basically, there's a lot of housekeeping that goes on in a system like this. It's very dynamic, and so that's what auto admin is there for. So those are the 4 components that we'll talk about.
Okay. So hearing the 4 components, we said request router, we said storage node, we said partition metadata system, and we said auto admin. And just kind of logically, my mind was expecting there to be something that like a query executor or something, like a place where the, compute gets done. I assume that's probably for like an individual query. I assume that's sort of a combination of the partition metadata system and the storage node. Partition metadata system basically saying, hey, these are the 2 storage nodes that are going to do this work for you. And the storage nodes then do the work of going and finding the stuff on a disk and getting it back. Because I was waiting for you to say, and there's the query execution module, or something like the thing that does the work of getting stuff.
Mm-hmm. Yeah. And I think it basically is handled by the mesh of the system itself, right?
Okay.
Kind of what you're alluding to there. So the front end
kind of spread across some of the different things that we've talked that you mentioned, these four pieces.
Yeah, I mean, in a way, so you have the front end are these request routers, and this is what clients are talking to, because clients, they should know like how stuff's partitioned, where things are and whatnot. So request routers, that's their job. So they're taking these incoming requests, whether they be puts or gets, queries, deletes, whatever that request is. It's then consulting it's working in concert with the metadata system to figure out, okay, what's the right storage node to go talk to, and then it forwards that request to the storage node. Right?
I think one of the answers is right there in the name. So router, request router, it's like it's literally routing to where the data is, routing to the storage nodes. Am I understanding you right? So otherwise, what's the purpose of the word router? What are we routing to?
Right. Yeah. Exactly. I mean, that's exactly. I mean, the primary purpose for the request router is given a input request, figure out, consult the metadata system, where does the data for this live, and then forward that request on and request that data from that particular node, and then retrieve back the results. It probably does some additional processing after it comes back, and then send it off to the client as a response. These storage nodes, I mean, it's not just a disk, right? I mean, there's software there for sure. So it's receiving these requests coming in. It's looking something up by a key, or it's consulting its index, and it's going and retrieving that particular piece of data.
Right. Yeah. And I think that's what I'm trying to get my head around. Maybe I'm thinking about things in terms of how load balancers work, or maybe I'm thinking about things in terms of how application server clusters work, or traditional database clusters. And I'm imagining, originally I was imagining, the request router is going to get me to some machine because maybe it's distributing load or something. But what it's really more like is that my DynamoDB, even though when I go and set it up, I'm saying to in the console or via the API, hey, make me a table. And I don't really see multiple machines or nodes becoming involved in the creation of that table. It's all totally a black box to me. But behind the scenes, maybe I've made a table of concerts coming up over the next 5 years, and like all the concerts of bands from A to G are in one node, and H to K are in another node, and K above that is in a third node, just for sake of argument. And then I make a request that for a band that's name starts with the letter R, that's going to be in the third node, and the request router is the thing that's going to get me to that node, and then that's where the work of getting the information out of the table is going to happen. Am I kind of starting to like get a sense of, because it's hard to get my head around, right? Because I thought I just made a table and I would just be talking to a system that knows about that table. But it sounds like behind the scenes, I'm talking to a number of different nodes, each of which may contain parts of my table.
Yeah, and it definitely goes back to like one of the key principles of NoSQL and why relational databases have problems scaling is in order to scale, you really have to scale out, and to scale out means you have to partition data, right? So that's really one of the core fundamental things that DynamoDB does. And so, yeah, these front-end request routers are basically, think of it as like partition managers or partition consultants or whatnot, right? They're the ones that are responsible for taking these input requests and saying, you know what you asked for really, like your data could be spread over like 10 different storage nodes or something like that, right? Or 5 storage nodes. And it's responsible for figuring out, okay, which one is it? And then routing it to it. So you can kind of think of it, it's almost like you don't really have one database. Maybe you have you have 5, right? And so the request router is the one for kind of figuring out like which one should it go to. So in that standpoint, it really is a router. I think it's kind of like, you can kind of think of it as like, it's almost like DNS in a way.
Yeah.
So it had basically that partition metadata system is the routing tables, right? And so it's consulting those routing tables to figure out, okay, what is the address that it should go talk to for this particular request.
Cool.
Right. So it's looking at that partition key or that global secondary index and saying, okay, what does that actually map to? Let me go consult the partition metadata system and then route that request accordingly.
Right on. I think this is making sense to me. I have so many questions still, but let's try to push forward.
Sure. And we've talked quite a bit about the request router. Maybe some additional things to talk about with the storage nodes is that there's 2 main types of storage nodes. There's the leader and then there's the secondaries. So you can think of the leader as the master. This is the one that always has the most up-to-date version of the data. And then they have 2 secondaries. And so these are the replicas, right? So it's 3 storage nodes essentially for every partition, if you will, of your database. And these replicas, obviously, they receive the updates from the leader themselves. So that's something to keep in mind. As I mentioned, the leader is propagating those writes to the peer storage secondary nodes. So a big part of this is like, hey, we need to know like what happens when there's a problem, right? What if the leader fails? What if a secondary fails and whatnot? So all that stuff has to be thought through, and there needs to be ways to handle that. So, in this particular talk, they shared that the leader is sending out heartbeat messages every 1.5 seconds to its secondary nodes. And if the secondary nodes, if they don't receive those heartbeats, the system will then perform an election to basically elect a new leader. And they use a algorithm called Paxos, which has been in the academic domain for quite some time. There's been a few papers written about it and describing it. It's a pretty common algorithm for dealing with these distributed systems. And when you need to elect a leader, a primary, a master, if you will, type thing. So they use Paxos.
So at this point, we have storage nodes, and each storage node is a leader and 2 secondaries. At that point, it feels like that stuff, while it is part of the overall architecture of DynamoDB, it's really part of solving for the availability piece and the reliability and like resilience of data piece. And it's like, and it feels like the solution there is really similar to what we may already be familiar with in terms of relational databases. I'm going to make 3 a leader and 2 followers of my relational database, and read replicas of my relational database, and that's how I'm going to make sure that if the main node goes down, I'll have backups like that. But it feels like that piece is like, we're going to do that for each partition of the DynamoDB, and who knows how many partitions we have, but within each, and what is causing, we have partition keys that decide how the partitions get divvied up. We don't know how many there are, but for each one, we're going to have this overall clustering architecture behind it so that we can trust that our data is going to be super reliable and super, just there. Is that a fair description of what's happening at those storage node levels? Yeah.
Yeah. This is definitely one, this is one of it's the patterns, right, for distributed systems. So when you scale out, that means you're talking clusters, and you're either clustering stateful or stateless resources. And both those have very common patterns that it's just a different for each application, you're just going to be implementing that same pattern in whatever way makes sense for your particular domain, right? So so just like RDS, right? If you want to run your relational database in a safe, secure, reliable way, then you better have replicas and you better be cross AZ. And you have to know when failures happen and what does failover mean and how does that work? And same thing goes for S3. S3, everything is replicated across 3 AZs.
That's the subtlety that I'm getting at. It's hard to put my finger right on it, but the subtlety that I'm getting at is that right now, the part of the architecture that we're talking about for DynamoDB is really related to the fact that it's a managed service. And so these decisions of how we're going to create availability have been decided by Amazon. Whereas if we were doing Mongo or something and we wanted to have each partition have 4 nodes, we could do that. And if DynamoDB wasn't a managed service and it was instead something that you could just install somewhere, then we might, decide that for our needs, we only need 2 per, a leader and a secondary per storage node. But that's not something that we get to do because DynamoDB is only a managed service. And this is how Amazon has set it up as a managed service.
Yeah, absolutely. And so this all goes to like what level of uptime availability they want to guarantee, right?
Exactly.
So, and this is why they do offer sometimes differences. So like you can go S3 one zone if you want. You can pay a little bit. It's a little bit less, but you don't get as good of availability versus the default of going across 3 zones. With Dynamo, there's no options there for right now, but it's one of those things where database is definitely pretty core, pretty critical. Cost wise. I mean, this is something that like I think most people would be doing anyhow, right? Like it's just
you would hope, but they totally wouldn't be, right? They'd be like, oh yeah, I think I have a read replica.
Yeah.
And we do backups. Wait, we don't do backups, but I think they're automated.
Right.
We've never tested a restore. That's what really happens in the real world.
Yeah. And of course, if someone like Amazon did that, then the first outage would be front page news everywhere. And it would just be, I mean, obviously Amazon knows how to run things and they've learned from experience and whatnot. So managed service, they get to decide, how it's architected, how many replicas they have, duplicates, what that is, because they also have to, keep it up and perform, live up to their SLA, right? That they're promising.
So you have a note here about replication, which we kind of talked about already, but also you have a note about strongly consistent versus eventually consistent.
Yeah, I mean, just with just about any kind of system like this, where you do have replication going on, there's almost always this concept of, do you want strongly consistent replicas or do you want eventually consistent replicas? And there's trade-offs between the two of them and between performance versus that consistency model, right? So strongly consistent in general usually means like we're not going to call this operation done until it has been replicated to all the replicas, right? So you're basically, it's taking you longer for you to basically commit that request because it has to do multiple writes and it has to wait for
potentially locking things up longer. If you need to prevent other writes from happening while you write that one thing or other reads from happening while you write that stuff.
Yeah, I mean, depending on how it's architected, chances are you don't have necessarily contention on that particular row that you're writing, but it may very well cause contention up at the request routing level type thing. So that's strongly consistent. The kind of probably the more normal mode for systems like this is eventually consistent. And so eventually consistent just says that, hey, we're going to write basically to the master, make that commit, and then we will report back that this request is done, return back to the caller while the replication is now happening after the fact. So it may be possible when that caller gets back the response that, yeah, your writes happened, if they actually try to read from one of the replicas, the data wouldn't be there yet. It would still be the old version because the replication hasn't happened. But eventually it will make it there. So that's the eventually consistent. So this reduces the number of writes that you have to do, the write operations you have to do whenever you are making a mutation, but it comes at the cost of, you may have some inconsistencies in your data for some short period of time. So it sounds kind of bad, right? Like to say, oh, eventually the data will be there. Eventually we'll be consistent. But in practice, it's really not a huge problem because you're already dealing with a very dynamic system. And depending on the data that you are using, if you're doing something like a shopping cart and trying to do a transaction or something of that nature, then the consistency problem becomes more important. But if you're doing things things like, hey, I created a new message, right? Or like think about like in a chat, like if you had a chat application, right, with chat messages and your clients are requesting the chat history. One person may request it and they'll see the new message and another one doesn't see it, but then they request the messages, a few seconds later and there it is. So to the end user, it was no big deal. They didn't really notice anything at all, right?
Right. And people are, everybody just refreshes their browser. Like, if they don't see the thing that they're expecting, it's sort of already ingrained from age 3 years old onward to try to refresh whatever you're looking at. So people kind of are trained in advance to deal with an eventual consistency.
Yep. Swipe down to see the spinny.
Yep.
Yeah. So maybe we should talk a little bit about maybe a walkthrough. So this was another thing and this is actually how they kind of started off the talk, was just kind of like doing a walkthrough for like operations for like to get a piece of data or to put a piece of data. It's a lot easier to do this in diagram format. That's one of the reasons why we kind of talked it through this way. So hopefully we're painting a better mental picture before we talk about it. And we've probably already touched on this a little bit, but just walking through like, what does it mean to do a get? So this is like, again, your caller is, maybe you have a table of chat messages or something like that, and it's now requesting the most recent chat message or the most recent message. And so what happens there? And so in that particular case, the DynamoDB client is making its call. It's getting sent to the front end request router, and the request routers are obviously duplicated. They're behind load balancers so that they scale out. The request router receives that request from the client. It's going to then authenticate with the caller. So it's going to do that dance to make sure that this particular caller is authorized to do this. And after that, it's going to be consulting with the partition metadata system. It's going to be looking at the item that they're requesting. Where does that live based upon the partition key or the global secondary index? And so again, doing that, like the equivalent of like looking up in the routing table, okay, where should this go? Mm-hmm. And once it figures that out, then that's when the request router will then go and retrieve that item from its assigned storage node. And so that's essentially the workflow for get request.
It's just in my mind, I'm just kind of trying to picture how this works. And I imagine that the request router, it has the query. It's able to figure out what the table is from the query. It's able to figure out, it maybe uses the partition metadata system to figure out what storage nodes the data that the query is requesting is going to be on. But then in my mind, it's forwarding kind of the whole part of the query that's relevant to the particular storage node to that storage node. And then that storage node itself is doing some work like, oh, okay, I just got this request for this data. That's my data. And I know how I've got my data organized. So I'm going to go reach into the file system at this location and grab, the next 10 blocks of data or whatever, based on my understanding of how the data is laid out inside of my node. And then I'm going to send it back. And so I guess what I'm getting at is that in my mind, the storage node is doing the work of knowing where the data is on disk and retrieving it, as opposed to just having the data and the request router or the partition metadata system saying, go get it. You know what I mean? Like in one sense, like the master overall computer can say, go into my network file system and grab this out. And another way, it's actually sending the query on, and the storage node is going, okay, now I'm going to go inside the disk and get the stuff I want out. You see how, like...
Yeah, I mean, again, don't think of the storage node as just a disk. I mean, it really is a database. There's a database engine there, right? So and all the things that go along with that. So it has indexes there. It has B-tree indexes for all the indexes on that particular table. And so it uses that to figure out, okay, where is this, how to go efficiently retrieve that data. It's a full up database engine.
Okay, cool. Yeah, that's now I have a better mental picture. Cool.
Awesome. And so then they also walk through just the corollary of how do you do writes, right? So what does a put look like in the system? And so a lot of that is pretty similar, especially the first part of it, right? So the DynamoDB client is making the call, it's hitting the front end request routers, the authentication's happening, it's consulting the partition metadata system to figure out what the leader is, the storage node leader for that particular piece of data. And then it's now the request router is going to forward on that write request to the storage node leader. The leader then replicates that request to its secondary nodes. And and the acknowledgement of the request is sent back after, and this is the eventual consistency model that's by default, right? So it's going to send back the acknowledgement after the write has happened to the leader and it's been replicated to at least to one secondary. So it does this in case of failure, right? So that there's not just one copy of the data, there needs to be at least two. Some other systems use things like transaction logs, but based upon this talk, it sounds like they don't necessarily, it wasn't totally clear, right, on what they're doing there. But this is the default behavior, is to write to the leader. The leader also then replicates to the two secondaries, and it will return back confirmation once it's been written to at least one of the secondaries, and the other secondary is not yet updated. Does that make sense?
So listening to this, I just have a hard time believing that all of this can be efficient, because we have a load balancer handling requests in front of the request router. The request router is talking to a partition metadata system that then is figuring out where a leader is to talk to, sending a query to that or a put to that, and then that's happening and actually writing to disk, and then all of it is traveling back up the tree and then back out to the client. And it all needs to happen lightning fast. And here I've got a JavaScript unit test that takes like 2.5 seconds to run. It's like, that certainly wouldn't be okay if it took 2.5 seconds for all that to happen. But it seems like a whole lot of stuff that has to happen. How can they possibly make that all fast?
Yeah, and truth is, I mean, this all happens in milliseconds, right?
Right,
so,
yeah.
But I mean, think about it. I mean, this is actually pretty streamlined. I mean, this is pretty bare bones and streamlined. I mean, this is built for speed and it's built for scalability. So, those front end request routers, they're built to be very, very fast. They're lightweight. They're caching information about the partition I'm sure they're caching partition metadata information, right? So they probably have the map there in memory on their nodes, right? So it's very fast to consult like which storage node I got to go talk to. They're on the networking connectivity they have with the storage nodes is obviously the best that you can get.
Sure, yeah.
Amazon is optimized for that. So these requests over to the storage nodes are very fast. And then the database engine on those storage nodes is very tight, purpose-built just for this. So
I guess one thing that still, though, to just kind of poke at this, is like one thing that I maybe isn't necessarily classically slow, but in my experience has been typically slow, is lots of JSON parsing. So I don't know if it's the case that, the request router receives a request that contains a big old chunk of JSON in it, but I imagine that it could be the case. If it is the case, like that this whole database is kind of just dealing in lots of JSON, wouldn't that also tend to be a problem?
Yeah, I mean, for the most part, like the JSON's not too much of an issue because as far as like the systems cares, it's just a bag of data.
Sure, yeah. If you're just getting a whole document out, it's like, yep, let me go get that bag of data and I'll send it to you. But if I've got to, traverse some JSON to figure out, okay, now deep inside here, I can see which storage node I need to route you to. Aren't some queries, don't they require that kind of processing?
Well, again, so you're going to be going off the partition key or the global secondary index on actually what partition you're going to. Once you got to that point, then the rest of the query processing is all there on that storage node. And then that's what those B tree indexes are for, like when you do want to access based upon a property inside your JSON document. So it's not necessarily parsing the JSON then, right? It's going off its indexes, its high-speed indexes that are implemented as B trees. So it's very fast, very efficient.
I think that's just such a fascinating thing because it's not intuitive. You have essentially a database whose whole world is storing JSON in it. That's what it's all about. And yet it's built to not ever really have to deal much in JSON. It's built to not have to parse JSON very much. Like the whole point of it is to avoid having to do that. Pretty wild to think about.
Yeah, I mean, if you think, it's really similar to like any database system, and like look at SQL. I mean, SQL is the same. And at the end of the day, like there's a certain layout format that it's writing data to disk in, and it's got to know offsets, and it's got to do parsing and figure out exactly where that stuff is. It's got to handle these queries that come in, and it's going against whatever fields that you're querying on. And so it has its indexes to go figure out, okay, where is it on disk to go retrieve this stuff? But at that point, it's just pulling back the record, right? So from that standpoint, JSON's really just a different way of unmarshalling the data.
Well, very cool. I think we're running out of time here, and we've gone a little long, but I want to give us a chance to, give you a chance to add anything more before we kind of shut it down. around. And
yeah, I think we made really good progress here. The only thing we really didn't touch on too much was the auto admin component, which is slightly unfortunate. It is a pretty important part of the system, and there's some really interesting problems that arise with a system like this. The biggest thing is just partitions. Like the longer the time that your database is up and the more data you put into it, the more likely that, hey, I'm going to get a hot partition, or partitions are just going to get too big. They're now performance is starting to become an issue, or I am starting to reach a limit. So what do? I need to actually split this up. And so this partition has to go from 1 to 2. And how do you do that, right? How do you decide when to do it? And then how do you do the data migration? How does all that, keep in sync and do it without all of it happen behind the scenes without clients knowing about it? So that's the reason for things like this auto admin component. That's one of the things that it does, along with other things, and just it detects failures, it detects corruptions, and just all that kind of general housekeeping. So it's not a very glamorous component, but it's really important. Like without that, like this whole thing just does not work as a service.
Right. That makes sense. And those were going to be some of my questions, is like, how do you know how many partitions you have? Does it even matter? How much data do you have to put in to have a new partition get created? And I think some of the answers to that are inside how the auto admin works.
Mm-hmm. Yeah, absolutely. And those are all, since Amazon runs this as a service, those are questions that they have, that they decide how to answer it, and they have thresholds, and obviously they have, heuristics and whatnot. And they're based upon various metrics, whether it could be like, performance, response time, could be, they don't want things to get beyond a certain limit from a size standpoint, from a partition size, could be things like replication lag, a bunch of different things would go into that to say, okay, you know what, we need to do a split.
Makes sense. Well, excellent. I think next week we'll talk a little bit more about Python and how that relates back to this architecture we talked about. So we'll do one more conversation about DynamoDB before moving on in the world of AWS.
Awesome. Sounds good.
Well, dear listener, you made it to the end. We appreciate your time and invite you to continue the conversation with us online. This episode, along with show notes and other valuable resources, is available at mobycast.fm/42. If you have any questions or additional insights, we encourage you to leave us a comment there. Thank you, and we'll see you again next week.